In the previous video we studied exponential growth and focused on what happens if the rate of change of y is proportional to y. But what happens if it's different? What if it's proportional to 4y? Then we'll be looking at something like this. Not much has changed. Our process is still going to be the same. We still just need to separate the variables, so we'll divide both sides by y. So 1 over y dy, and multiply both sides by dt equals 4k dt. And we'll just trust our process of separation of variables. I'm going to integrate both sides, so the natural log of the absolute value of y should equal 4k, because those are just constants, t plus c. So we've got a bunch of constants and one variable t. And if I convert this to exponential form, the absolute value of y is equal to e to the 4kt plus c. And I know that e to any power has to be positive. I also know that by exponent properties I can rewrite it to mean this, and e to the c power is just a constant itself. Now, it might be a different relationship, and I just have to be prepared to adjust, but my process is really the same. What if the rate of change of y is proportional to 4 minus y? Well, I still need to separate the variables. In this case, I'm going to divide both sides by 4 minus y and multiply both sides by dt. And now I'm just going to integrate. When I integrate the left, I'll have negative natural log of the absolute value of 4 minus y. Don't forget the chain rule on that. Equals kt plus c. And if I divide both sides by -1, then we'll have the natural log of the absolute value of 4 minus y equals, well, remember that k is just some constant, so I don't know anything about it. It's still a constant when I divide it by -1, so it's just kt. And remember that c is just a constant, so since I don't know anything about it, when I divide it by a negative, it's still just some constant that remains unknown. If I convert this to exponential form, then the absolute value of 4 minus y is equal to e to the kt plus c. But e to any power has to be positive, so I can drop the absolute value bars. 4 minus y must equal e to the kt times e to the c. Notice I'm taking some liberties here. E to the c is just some constant, so we'll have 4 minus y equals c e to the kt. And if I add y to both sides and subtract cekt from both sides, we'll end up with 4 minus ce to the kt equals y. And the sign of c will take care of itself. It may end up being positive, it may end up being negative. It'll work itself out. We've solved this. Notice again we're just using separation of variables. Let's consider two more examples like this. What if the rate of change of y, what if dy dt, is inversely proportional to y? Well, I can just write this up and separate the variables. This tells me that y dy, when I multiply both sides by y, equals k dt, when I multiply both sides by dt. Need to integrate, so I'll end up with 1/2 y squared must equal kt plus c. If I multiply both sides by 2, then I know that y squared equals 2kt plus c, because 2 times a constant is still some constant, and when I take the square root, I'll end up with 2kt plus c. It's probably a better bet to stop here at y squared equals 2kt plus c That way I don't have to deal with the decision of whether I'm dealing with a positive or a negative quantity. I can just keep the relationship that way and take the square root when I need to. Final example of this type, and then we'll look at a problem, is what if the rate of change of y, if dy dt, is proportional to the square root of y. Again, not much has changed. I'll divide both sides by the square root of y, so 1 over y to the 1/2 dy, multiply both sides by dt equals k dt. Now I need to integrate this, and this will be 2y to the 1/2 equals kt plus c. Dividing both sides by 2, y to the 1/2 equals 1/2 kt plus c. And when I square both sides, y equals this whole thing squared. Now let's consider a problem. In this problem, there's a tin can. It's filled with water, and then a hole is punched out near the bottom. And the water leaks out quickly at first, and then more slowly as the depth of the water decreases. Right, so the rate of change is changing. In physics, it can be proved that the rate of change at which the water's height changes. So dH, what happened? So dH dt is directly proportional to the square root of the height. Write a differential equation which states this relationship. We've done that. Part B, at time t equals 0, we know the height is 12 centimeters. And we also know that dH dt is equal to -3 centimeters per second. So now we can find the value of k. Because what we know is that -3 equals k times the square root of 12, or -3 divided by the square root of 12 equals k. Solve this equation to solve the actual differential equation. So recall that we just solved this, so we know that dH dt equals -3 over the square root of 12 times the square root of h. And we can solve this by separating the variables if we'd like. Some of you may already remember from a previous problem what we're going to get. I'll solve by separation of variables. So I know that 1 over the square root of h dh should equal -3 divided by the square root of 12 dt. And when we integrate both sides, we're going to end up with 2h to the 1/2 equals -3 over the square root of 12 times t plus c. If I'd like to solve this for h, well, h to the 1/2 power equals -3 over 2 times the square root of 12 t plus c. And remember that when t equals 0, h has to be 12. Right, so that'll be important in our work. That when t equals 0, h is 12. This tells me that the square root of 12 should equal c. So my equation is that h to the 1/2 equals negative 3 divided by 2 times the square root of 12t plus the square root of 12. So h is this entire messy looking thing squared. What kind of function is this? Notice that we just expand this equation, we end up with just a normal quadratic. And finally, right, or normal quadratic. Finally, the question could be, well, when does the can become empty? Well, the can is empty when the height is 0. So here's my quadratic. My options are to try to factor this, or I could complete the square, or I could use the quadratic formula to solve this quadratic. Let's see. Multiply everything by 16. I might be able to factor it, but I think we'll just use the quadratic formula. Actually, if we go back to here, it's even easier to solve because we just want to know when does that equal 0, which means we want to know when does just the thing itself equal 0, because only 0 squared is 0. So when are the two pieces equal to one another, or multiplying both sides by 2 root 12, when does 3t equal 24? This is when t equals 8. Our time in this case was seconds, so this would be 8 seconds. So there's our example from other kinds of exponential growth.